size, very tiny sensors. Sensors about 100 microns in size, little tiny devices for neural recording. And today I want to tell you about our goal to build little tiny systems that learn, right? Components that are made in very classic microelectronics platforms like semiconductor CMOS processing, but adapted to concepts from physical neural networks. And I want to tell you about one particular use case for these electrical networks, although we build them generally as being a substrate for doing diffusion models. So basically the things that we use to make these horribly energy intensive images, like the things produced by ChatGPT. So Peter did a phenomenal job of introducing this session. I'm going to steal extensively from him and the wonderful reviews that he's written about broadly why physical systems, why these classes of networks, and what is it exactly that we're trying to do. And so, broadly, I think the overarching idea for a lot of the talks that we're going to see today is that any physical system, by virtue of what it does, solves usually some form of a task that we might consider a computation. So a really classic example are electrical networks, where intrinsically an electrical network, like say this network of resistors, is known to find solutions in voltage space that minimize the electrical power dissipated for a set of voltages that you put in. And so every time you've hooked up an electrical network of resistors, it's essentially solved some form of a minimization problem, specifically on sets of power, and that idea could be turned around as a way of sort of solving optimization problems. And so a lot of fantastic work has been done by my colleagues, Doug Durian and Adrian Liu. The person who actually did it is Sam Dillon, who's sitting over there, to take this idea and turn it around to build networks of adjustable resistances that could be, say, trained to solve specific optimization problems. So that if you put a voltage in, it identifies a particular minimum in power space, and you could train it to solve tasks that you want. Now this electrical network fits into a broader family of stuff. It's all kinds of other networks of physical systems you can build. And I'm going to again steal from Peter. At this stage, I think it's fair to say that almost every physical substrate that at least I know about, I can find some paper where somebody has used it to do some form of learning, right? Like you can make learning systems out of mechanical networks, you can build them out of molecules, you can build them out of optical systems, you can build them out of electrical systems like we do. And I think if I went through all of these different spaces, I could probably find some example of somebody doing MNIST as well, right? That you could go take specific problems and do them in some specific set. And so I think one thing I would argue is at this stage for the field, the question of whether or not you can build a neural network, say, out of X is maybe not an interesting one. I think the answer seems to almost always be yes, right? It's not that hard to build something that has a linear matrix and has a nonlinearity and then force it to do some kind of learning. The question increasingly is, what are they good for? Are there specific questions, problems, tasks that are well posed to the specifics of the physical substrate that you're interested in? And I think there's two ways you could attack this problem. One would be sort of coming at it from the top down, saying, okay, well, this is the abstract computation I'd like to do. What are the requirements of it? How do I match those to physical objectives? And the other might be coming at it from the bottom. This is surreal, this bear. I realize I'm standing right in front of it. So for all of you, it looks like I've either made a friend or I'm about to be eaten. So the other way you can come at it is from the bottom up, right? Is to say, okay, this is the particular system I'm interested in. What exactly does it do? And do those look like other types of computations? And so for this talk, I'm going to focus on both of those kind of at once. I'm going to single out a particular physical system. I'm going to single out a particular computation. And then I'm going to try to build the bridge from both ends, right, and argue that they match. And so the system I'm going to single out are electrical networks. One's kind of like this one, built by Sam. I've chosen this image because I think it's particularly meta for the picture of him to be working on the thing that I'm telling you he works on. But this is a network built of these self-adjusting resistances. From the physical point of view, it's basically just a network of resistors with a little bit of nonlinearity. And the question we could ask is, what kinds of problems could this thing solve well? Now, if you look at it from face value, you might say, well, I don't know. A resistor network is just a linear network. It's linear inputs. You put in voltages on one side, you get voltages out on the other side. But that's not quite true, right? It's not exactly linear because you can't build any linear output that you want. There's actually some restrictions associated to the kinds of input-output relationships you can have. Really trivial one, right? If I put 1 voltage in as my highest sourcing voltage, I can't get any voltages bigger than that. And so you can build linear networks with some kind of restriction. And you might ask, what sorts of restrictions are those, right? Do they match to particular cases where those restrictions are actually useful, where the things that I'm excluding from stuff I can learn are things I don't want to learn anyway, right? And I'm going to make a jump and argue that I think one particularly good class where electrical networks maybe stand out and things that are like it would be in solving this family of problems, diffusion models. So diffusion models are the backbone of image generation. They're basically the thing that you use in most times you query ChatGPT to draw you a picture of, say, a rabbit. And if you don't know how they work, they're really quite interesting because they're remarkably physical in their motivations and their origins. In fact, if you look in the literature, some of the origins of these models come from looking at ideas in non-equilibrium statistical physics, which is really quite cool, and I think for this community should be attractive. So if you ever get curious, like how do you actually make an image of say, this cat, the way that these algorithms work is the following. Is you take a bunch of data of cats, a bunch of images, and it gives you some sort of sampling of the distribution of things we might call cats. Now you don't know how to sample from it, but you do have a bunch of examples of what that thing is. And so what you do is the following strategy, is you take your data and you progressively add noise to it, so you almost do like a random walk in pixel space. So from a physical point of view, the way you can think about it is you start out with some point in pixel space representing this image, and then over a series of time steps, you add white noise to each of those. You take a little random walk around pixel space. And if you were to look at it, you would see your cat getting noisier and noisier and noisier, until eventually it turns into what we all know, just pure static, right? If I keep adding noise, eventually the outcome is noise. Now, why do I do this? Well, two reasons. One is that the final product of this process is a statistical distribution that I do know how to sample from. In this case, perfectly uniform random noise on data, right? And so the final outcome is something that's known. The second is that by watching this process of forward evolution, you can learn a statistical operator that will take you backwards in time. And so for this particular example, if I just added white noise, it's known that you can build a time reversal of this operation by running a different random walk, where you again take a point, you add white noise to it, and you also give it a mean motion, which is given by the gradient of the log of the probability of the forward random walk. And if you're a statistical physicist, you can kind of squint at this and convince yourself this is right, because if you think about it, where would this thing want to equilibrate? Well, if I didn't change this over time, you would equilibrate to matching P+, because this is acting sort of like an energy landscape, and I go to the exponential of the energy, exponential of the log is the same function, so you equilibrate to this distribution. But if I let this evolve so that I'm doing this at each time step, I'm always kind of near that distribution because I'm always near the equilibrium. And so I kind of nudge myself backwards in time to the original distribution. Now, why is this valuable? Well, if you wanted to learn this backwards in time evolution, the only thing you really have to know is essentially an estimate of the gradient of the log of the probability of the forward process. Which means by watching me add noise to this data, I can generate a way of learning this backwards operation. So I get two things, right? One is as I noise this data, I build a training set to learn this backwards in time operator, and then I can close the loop. I could say, suppose I wanted to draw a sample from the original distribution, well then what I could do is draw a sample from this final noise, use this backwards in time operator, and then I could walk back in time to draw a sample from the original distribution on the other side. And this is procedurally how these things work, is essentially there's different ways of framing this problem, there's different ways you can learn this backwards operation, but the gist of it is, you take a data set, you add noise to it moving it forward, you learn how to undo that process by watching the forward evolution process, and then by sampling from this final random distribution, you can run that time reversal operator to go back in time. Now, this is pretty cool. There's a bunch of really interesting mathematics that goes with this, but at this point you may be wondering, great, fine, what the hell does that have to do with resistors? I mean, why on earth would you believe that the humble resistor network, these dumb things, would be able to do that sophisticated job? Like, what possible connection is there between backwards Markov chains and linear electrical networks? I think it's actually quite a good one, and somewhat remarkably. And if you don't appreciate why, it's probably because you're not this guy up here. So this is Joseph Duke. He was a mathematician in the 20th century, and he was an expert on two topics. One was potential theory, so the mathematical theory of electrical networks and solving Laplace's equation, things like that in different forms. And the other was stochastic processes, so random walks, Markov chains, things like that. And midway through his career, he decided to write a 5,000-page book arguing that these are two sides of the same thing. It is literally brutal. It's one of the only books I've ever not read. So like, I opened it and I was like, this will be cool, I'll learn this. And I got about like halfway into it, I was like, oh my God, this is like, this is madness. But he made a very, but he made a remarkable career out of this idea that, a lot of problems in potential theory have connections to Markov chains and vice versa. And we know examples of this. Maybe if you did a physics degree, you know that there's these things like you can solve, Laplace's equation by doing random walks, stuff like that. But we can see sort of the high level of what we need for this case by looking at some of the qualitative features of electrical networks and comparing them to the statistical representations of random walks. So, for example, the restriction that we see in electrical networks, of the kinds of voltages you can read out, are a lot like the restrictions that you would naturally have in probabilistic systems. So take, for example, this very simple electrical network, crossbar array. It's just got a set of voltages that I'm setting on this side, and one set of intermediate nodes in the middle. And so let's say I set a voltage 1 here, 0 here, 0 here, 0 here, and I can read out the voltages on the other side. This is essentially a voltage averager in disguise. And each of these intermediate nodes is going to produce a weighted average of the input nodes. So if I wanted to read off the voltage at Vj, I note that that's basically, you look at all the voltages in Vi, the ones that are on the input side, you weight them by the conductance that connects them back, and then you actually normalize it. You divide it through by the sum of all conductances. And so if you look at the output, the restrictions on the things that I can actually solve for, the kinds of linear problems I can produce, satisfy the following conditions. That every voltage I could read off the intermediates is bounded from 0 and 1. And then if I were to sum over all of the possible choices I could have picked for voltages on the input side, that too has to sum to 1 on the other side. And if you squint at this, this really almost kind of looks like a probability law, right? It basically says that whatever I get as the final output from this input probability, it's the product of two numbers, each of which is bounded between 0 and 1. And if I were to sum over all the possibilities I could have chosen, I again have to have a constraint satisfaction on 1. It looks like a joint probability, right? Probability here, conditional probability, final output on the other side. Now Duke went one step further, and what he showed very convincingly, I will state, is that if you were to take an electrical network and you grab some set of nodes and you held them at voltages of, let's say, 0 and 1, there's a very clean statistical interpretation in terms of what you're doing. So let's say I take some random electrical network, I grab some nodes, in this case I'll grab this one down here and this one up here, and I set them at voltages of 0 and 1. Now I'm free to choose which one is 1 and 0, right? This could be 1 here, that could be 0, but my only restriction is that things I'm calling boundary nodes have to satisfy the 0 and 1. If I do that, any intermediate voltage I read out can be interpreted as being the same thing as starting a random walk at that site and asking whether it reaches the 1 node voltages before it reaches the 0 node voltages. So in other words, if I were to read off the voltage electrically at this site, it's equivalent to taking a random walker, letting it walk around this network with weights of transitions dependent on the conductances, and then if it hits the 0 first, or it hits the, if it hits the 0 first or it hits the 1 first, the probability of either of those two events. And so there's a very clean way of thinking about these that lets you go back and forth between these two different points of view. I could either solve this problem by saying, well, I have an electrical network, give me the voltages and then compute the value there, or equivalently, I could say, okay, initialize a bunch of random walkers here, and then take the average of all the times it got to 1 versus the number of times it got to 0. Those will be the same number. They're two sides of the same coin. They're two different ways of solving the exact same problem. Now, from my point of view, this is interesting because it means that the one electrical network has a foot in each of these two different domains, right? On the one hand, it's something that's very easy to engineer and build and work with because I know how to source voltages, I know how to manipulate conductances, I know how to play all kinds of games like that. But on the other hand, if I interpret what the voltages mean in a very specific way, I can relate them to statistical properties in random walks, which is, after all, ultimately any diffusion is a random walk. And so it gives you some hope that you might be able to do the following. This is kind of the problems that I'm actually going to talk about. Would it be possible to build an electrical network that you can feed stochastic data, so examples of, say, some Markov process, some random walking chain, and it could learn a representation of that random walk that you could use to, to functionally evaluate probabilities, or to sample from it, or to say, I don't know, run it backwards in time, something along those lines. And there's hope that this could be doable, right? That, there's really this one-to-one correspondence. It may just boil down to interpreting the voltages the right way and building the right kinds of networks, right? It may be an architecture choice. Like, how do I pick to lay this thing out, and what kinds of learning rules should I do? And so I'm going to use the rest of my talk to tell you about one particular algorithm we figured out for doing this, show you some examples of it working in practice, and then talk a little bit about actually building one of these like for real. Okay, so how might you do this? Well, everything I want to tell you about from here is work done by Sophia, my graduate student, who's sitting over there. So be sure to ask her lots of questions about this afterwards. But this is the idea that she came up with. This is sort of our first pass at solving this goal. So what we do is the following. Is we take some stream of stochastic data, so you can just think about this as a computer simulation of something that's random, right? So like event A happens, then event B happens, and the probability of B is conditioned on whatever happened for A. So you can think about just like a favorite one, random walk, conditional probabilities, whatever. And we feed this data to an electrical network to learn it in the following form. We build two sides of the network, one representing the state you were just in, and the other representing the state that you've now transitioned into. Right? So in this particular example, if say I just fed it this pair, I would say a voltage over here, or state over here, is representative of the thing that just happened, and a voltage on this side is representative of the state I was just in. Now to train a representation of this stochastic process, we do the following. We feed it a pair of a transition. So in this case, let's say A just transitioned to, I don't know, C. And then we isolate the part of the network where we're only looking at edges that connect to the new state. So we ignore all of the edges of the things that could have been, and we just focus on the edges that link the state you are now in to the possibilities of what you were previously in on the other side. What do we do next? Well, we create a voltage sourcing pattern. So we put 1 volt at the state you actually were previously in, and we put 0 volts on the states that you were not. And then we read off the voltage at this one free node, the node representing the state you transitioned to. So we'll call that V sub I throughout this. And we call this electrical network state the free state. So it's one evaluation. Then what we do is we change our sourcing pattern to a second configuration of input voltages, which I'll call the source state. There's another way you could call this with clamp, but for the purpose of this talk, we'll call it source. And what we do in this case is we take all of the possible things you could have been, pull them all at ground, and now we put a voltage on our one intermediate node of the state you transition to of a small nudge factor eta times 1 minus VA, where this is the voltage you previously read out on the free state. So you have 2 different electrical configurations. Yes?
So you operate this digitally or analog?
This is, you can think of as an analog circuit, just be doing this. Now the talk I'm going to show you mostly simulations, but at the end this will be an actual electrical network. So we're getting there. But yeah, think of this as an actual resistor network. Yes?
I was wondering, with the source step, how perfect a time reversal symmetry does it need to be? If you have any small non-
Bear with me.
Okay.
I haven't even shown you that works yet. Thank you. I appreciate it. It's a big vote of confidence in my talk. Because we're okay. So then what do we do to train this thing, to learn something? We do the following, which is if you are connected to the state that you just transitioned to, so again, we ignore these edges, things that did not happen, you update your conductance as follows. Your conductance rate of change is basically, it's a very simple contrastive learning rule minus the voltage drop across that edge in the free state times the voltage drop in the sourcing state. So you simply read off the voltage drop here, say in this state, then you read off the voltage drop here, and then this edge is updated to be basically minus the product of the two. That's it. That's all we're going to do. Okay, so fine. Why? What does this rule do? What is its purpose? Now, maybe some people have convinced themselves that this makes sense, right? Because it does look a lot like, say, coupled learning or equilibrium propagation, right? It has kind of a physical learning network vibe. But it's still worth asking, what is this thing actually learning if we do this, right? Of course, we can make clamp in free states, and we can make some Hebbian type learning rule, but what exactly does it learn? It's kind of interesting. What does this rule do? Well, to get at that answer, you have to ask what kinds of changes can it make to that conductance, and how likely are each of the two of them? Because unlike a typical training set, right, these are now probabilistic, right? There's a probability that I'm the special edge that represents the transition that took place. There's also a probability of not, in which case I see two different sourcing conditions. And so you work through very quickly and see what they are. Well, if you are only looking at edges that are connected to the event that took place, there's two possibilities. Either you're the special edge that links the two states that actually represented the transition, so the thing that you transitioned to and the thing we were previously in, or you're not, right? You link the thing that you transitioned to something that you weren't in previously on the other side. And so you can simply write down the two updates themselves. Grind through a little bit of math, and you can compute that if you are in the transition that took place, your update rule is the following. You see a conductance, which is your nudge factor times 1 minus the voltage of free state squared. This kind of makes sense because this is always positive. So it says if you represent the transition that took place, conductance goes up. It makes this probability more likely, makes this connection stronger. If on the other hand, you're in the one that did not take place, your update rule changes to eta times 1 minus VI times VI. And so this goes down, right? It acts to decrease the conductance on the other side. So qualitatively, this is kind of reasonable. You boost conductances for transitions that occurred. You smush conductances for things that didn't. If this is being held at 1 volt, it makes this connection closer to 1 volt. So it's saying if this transition happens more often, then having an event having taken place here correlates more strongly to having an event taking place on the other side. But still not convincing, so it's still qualitative. What does it actually mean in terms of like solid math? Well, you can do a little bit more grinding of chalk. In the interest of time, I will go quick. I won't go through this in detail. The key idea is this one at the bottom. If you work through, you can take the ensemble average of this learning. So you basically say, take those two different possibilities, multiply them by the probability of each of the transitions taking place, sum it up. You do a bunch of fancy algebra, and you wind up down here at the bottom. And what you'll find is that the average change of your conductance is 1 minus VI. This is just your estimate of voltage, times the probability of the second state. We don't really care about this prefactor because it's strictly positive. It doesn't really do anything harmful, times this, and this is the important part. Ti given j, this is the actual conditional probability of the Markov chain. It says the probability that you were in state I given you transition to state j minus the voltage produced in the free state. And so what does this learning rule do? It trains your network so that whatever voltage you read out here is the conditional probability that you were there. It learns the backwards conditional probability, the thing you would need if you, say, wanted to run this Markov chain backwards in time.
Is that the contrastive part, or
What's that?
is that the contrastive part, or is contrastive something else? Previous slides said contrastive.
I mean, by contrastive, I mean that you're showing you two different examples, the thing it does and the thing you want it to learn. This just falls out of the, let's go to the next slide.
Yeah.
See what we
Yeah,
got.
thanks.
If you don't like contrastive learning, like maybe you don't, I don't know. There's a different way that you can see the same result and also that you can derive it. So the way we derived it was by basically arguing by analogy from things we know about contrastive learning and then turning the crank on the algebra. There's a separate derivation you can do, which is the following if you're more stats oriented, which is to say you could rewrite the learning rule I just showed you in terms of indicator functions. So a function that's either 1 if the event took place or 0 if it didn't. And structurally it's equivalent to this form. Basically this says the indicator here is conditioned on the second state, so it says don't do any updates if you're one of the edges where the transition is not connected to the state that occurred. There's a second indicator on the state that you actually came from, and this implements the two different possibilities for your learning rule, the one case where it's 1 minus VI squared and the other where it's 1 minus VI times minus VI. Now, if you wanted to, another way to phrase the task you're doing would be to say learn a log likelihood maximization, which is the way you would normally do it in statistics. And for this problem, if you just wrote down the log likelihood of a given transition, it's functionally equivalent to this. If you took its gradient, you get something that looks like this on the bottom, which again has your two indicator functions. It has a 1 minus, this is basically the voltage at the intermediate node. And so you can note the rule that we wrote down is basically the same as saying, update your conductances proportional to the gradient of the log likelihood. And so another way of thinking about what you're doing is you're doing gradient descent on the log likelihood. You're just doing it online. So two different perspectives depending on whether you're more in the contrastive learning physical networks camp or more in the stats camp. They're both equivalent and they both can either not. Okay, so does this work? Let's find out. It's one thing to say a bunch of math, blah, blah, blah. Point is, like, what happens when you actually run this thing in practice? And so I'll give you examples of increasing level of difficulties. One caveat is that these are all going to be simulations for the time being. Come back to that at the end, you'll see why. But it's good to test things in simulation before you invest a bunch of effort in hardware. Maybe not surprising as an idea. Okay, so what's the simplest thing you could do? Well, one really simple example would be to make, very basic conditional probability structure. So consider the following. Let's say we had two random variables. We'll call one x, and we'll call the other by the label a and b. And we could show our network examples of a system where the probability of selecting a or b is, say, conditioned on when you run an x. And we'll build our distributions as follows, so that if you wanted to run it backwards, it would be equivalent to having basically two bell curves, right? That if you knew A, you would get one bell curve. If you knew B, you'd get a different bell curve. But what we're going to show the network are examples of things running forwards, right? We're going to give it an example of X, so I just pick one position here. It could have come from this Gaussian or from that Gaussian, and then I show it the label on the other side. And it's going to be tasked with learning the backwards conditional so that I could then sample from this very simple distribution of A and B, where they're both equiprobable, and then presumably reconstruct each of those bell curves individually, although the only data I gave it was the two of them together, right, the composite on top of each other. So does this work? Well, on the right, you'll see the example. So these dots represent what our network is predicting for each of the distributions. Solid lines are what it should get. And each step in this movie is going to be as we give the algorithm more data to learn. So off it goes, learning, learning, learning. And then you can see it nicely equilibrates to those two distributions with a little bit of fluctuations around it, because it is a stochastic algorithm at the end of the day. If you want to be quantitative, you can take measures like, say, the KL diversion, so essentially computing the number of bits that you missed. You get a nice graph that looks like this, where you see a nice exponential decrease as the data set size gets bigger and bigger and bigger, so you're crushing it, learning this distribution, and then eventually it flattens off. And that represents this sort of fluctuation stage. And we know that if we decrease our learning rate so that we're averaging over more data sets per update of the weights, this floor actually goes down. And so we can control this parameter as well. If you want to make it more precise, you can actually do that. So this is good. It's encouraging, cool, but it's kind of a trivial example. Could we do something a little fancier? And so in our quest towards making images, what you might say is, okay, let's try and reverse a random walk. Right? Instead of just doing one step of this chain, do multiple steps, right? And of course, you can think about a random walk as being a sequence of conditional probabilities, where at each step in the walk, right, if I know I'm here, there's some probability I transition to this, and then there's some probability I transition to this, and then some to that, and then some to that. And so equivalently, what I might like to do to learn the backwards process would be learn each of these reverse conditions, that if I am here, I can estimate what the probability was I was in one of these other states. And then I could run that process backwards to try to run the random walk in reverse. So here's what we do. We run a bunch of simulations with random walks. Here's a very simple example where basically you're initializing from one of three locations, and then the rest of it is just a uniform random walk on a lattice. So you can step to the left, step to the right, equal probabilities. You can also stay where you are. And then we feed this to a sequence of these learning networks, where each one of those networks learns one step of the walk. Right? So each one is responsible with learning each little phase of a backwards process, so that you could infer the state you were previously in, given you're currently on this state here. Now the key idea, of course, is that the place random walk ends is uniform randomness, and so if I wanted to say run my forward walk in reverse, all I do, sample from the final distribution, which is uniformly at random, feed it into this chain of resistor networks, and I should be able to go back to my initial distribution on the other side. So let's see if it works. Here's what our network spits out for time reversing this markup process, and I'll show you movies, each one where we've increased the data set size. So initially, it's obviously terrible, and it has no idea what it's doing, and it just creates a random walk that stays uniform. You feed it a couple hundred examples, and it starts to learn some of the features. So you can see it's starting to figure out that actually, yeah, these need to be a little bit more probable, but it's still pretty fuzzy. You feed it about 100,000 examples, and it's actually getting pretty good, right? To the point where it's almost indistinguishable between these two different data sets, right? If I showed you just these two pictures and I colored them the same way and said which one's forwards and backwards, you'd have a hard time of being able to figure it out. Again, you can be quantitative. You can plot things like the KL divergence for each of these cases, and you find out, indeed, it does learn how to time reverse this process. So what are we showing here? We're showing essentially the KL divergence in a couple different forms. One is comparing the KL between the probability of finding the walker along a given time slice at different slices of time. So this orange curve is the distance between what the backwards process predicts at time 0 and what the forwards process had at time 0. This would be the distance between the backwards at 3 and the forwards at 3, etc. And you can see they're quite good, right? It actually does learn to correctly reproduce what the forward distribution said when you run this thing backwards in time. You can note that it also holds for the mean, and somewhere again around, I don't know what this is, 10,000 data sets that you've shown it, you wind up with things where essentially the learning process is saturated. You really can't tell the difference between this thing running forwards in time or the Markov chain being learned to reverse it through the electrical network on the other side. Okay, so this is cool. Still not images. Okay, we're still not there. And we're in early days, so we're not quite going to be able to beat ChatGPT quite yet. So we figured we would target the most important use of image generation on the internet, just go right for the heart of the matter, and focus on building one class of images first, which of course is cats. 99% of the use of the internet is of course cute pictures of cats. It's overwhelmingly what we use it for. And so we should focus our efforts entirely on generating images of cute kittens. So how do you do this? Well, there's one other trick that you need to know, which is to make this problem tractable. And that's that any image, right, is a huge space, ginormous, right? It's 2 to the however many pixels you have times however many colors, right? Giant, giant space. And so we probably don't want to random walk on that space directly, right? And in fact, even the machine learning people at Google don't do this, right? It's just an intractable problem. So what we do first is we're going to build a compression of this image down to a simpler space where we can do our random walks and then apply our algorithm there. And so here's what we did, is we took a data set. There's a data set for everything, by the way. I again am confident you can literally find a data set of anything, and in fact there's a data set just of pictures of cute cats, which is awesome. So we take this data set and we feed it to an autoencoder where the middle layer, the latent layer of the encoder, is essentially a collection of discrete states. It's a vector quantized autoencoder is basically the architecture that we're using. And then we train a second half of this autoencoder that learns how to take this intermediate latent representation of discrete states and translate it back into images. And so in the original data set, we essentially just train something where it learns how to take pictures of cats into pictures of cats with an intermediate representation that's smaller and discrete. And then to train our algorithm, we do the following. We take our original images, we progressively add noise to each of those images, right? So we take our cats, fuzz them out, and we feed those fuzzed images into the first stage of the encoder at each one of these. Right? And this gives us a statistical distribution in this discrete encoder space, which is representative of taking a random walk on the original image set. Then we come along and we use our learning network to learn an intermediate representation of how to walk backwards along these discrete states, so backwards in time, and then you can take the system, feed in randomly generated noise, and hopefully it will spit back out an image of a cat, right? That's basically the architecture. So let's see if it works. Okay, so here's the forward process. We'll call this cat to noise. Take a picture of the cat, add noise to it along each step, and you get something that looks like this. Truly the stuff of nightmares. And great, bear with, I'm not sure how this is much better. And then we can look at the reverse process, which is noise to cat. So there we are producing our cat image on the other side. All of this, by the way, produced with resistors, right? With just resistors, the most boring of electrical elements. Once you have this, you have, of course, a machine for producing images of cats at will. And so Sophia's now made 100 cats, something like that, probably more.
Way more.
Way more. Shown me 100 cats, I'm not worried. So, of varying levels of cuteness. Now, you might say some of these are better than others. I think it's a fair statement, unless you really like the cat, this one maybe not so good. Some of them are better. And part of this has to do with extensions of this algorithm that could improve it, right? Now what's cool is that the big issue here is that we're treating each of the pixels in sort of our latent space as independent variables. And they're not, they're correlated, right? There should be spatial correlation along those. But we're confident that actually the approach we've come up with ought to be able to handle this, because at the end of the day, what we're really just learning are conditional probabilities, right? With a little bit more work on the architecture of how we build these resistor networks, we actually think we can encode both the correlations in time from the random walk and the correlations in space from the image itself. So a couple of interesting extensions we're playing around with are following, extending this to sort of Markov random fields, so things that are both random walking in time but also correlated in space, so you care about your neighboring pixels. Again, our algorithm, if you think about it, doesn't really know which way is time, it just is learning whichever correlation you ask it to, so you can point it in different directions. We're looking at applying this for, say, hidden Markov models, really common in robotics. I think this may be a really cool use case where low power, chip-based learning would be very valuable, like robot speed, low power, it's good. Another cool extension is mixed data types. So you do image generation, you type in the word cat, right, and that's how it knows how to do it. That means it has to learn conditional probabilities under the text of images. But again, we don't care, we're just learning conditional probabilities. So this may be another fun extension. So briefly, in the last 2 minutes, I'll tell you about one other really cool thing, which is of course the following. Okay, this is great, but like I said, this is all simulation. How do we do this for real, right? And we're probably not going to want to challenge NVIDIA with this. This is really, really cool science, but it's not really scalable for producing lots of really high quality images. I'll say one of the other cool things Sophia's been working on is actually building a chip-based version of everything I just told you. I don't have an enormous amount of time, so I will go through it very, very quickly. The gist of it is we replace all the resistors with subthreshold transistors. So a subthreshold regime are transistors that basically work by barrier hopping. You get a current that's essentially proportional to differences in the voltage on one side times the gate voltage. Why is this a good idea? A couple reasons. One is that currents in these systems are insanely low. They typically range from, say, picoamps to maybe like a microamp. And they operate over about 100 millivolts of swing, which means that the powers are wildly tiny if you can build your system as it's like 1 microwatt to picowatt per edge. The other is that you have a very high degree of conductivity expression because you vary that exponentially by controlling gate voltage. That's important if you want to very accurately pin down your probabilities. And the last is that you can connect them to resistor networks by doing a cute trick, which electrical engineers figured out in the 90s, which is that if you take this IV characteristic and you just pretend that instead of voltage, e to the minus v was voltage, it's the same form as being a linear resistor network. It's just in this transform variable set. And so you can exploit this to solve linear problems by doing it in the transform space and then building hardware to do it on the other side. Remarkably, everything I told you about in terms of the learning rule can also be implemented in subthreshold transistors. If there's an EE, I'm happy to talk with you about the circuit, but I'm sure probably nobody cares. Otherwise, I was really proud of this, so please do if you are interested. What's noteworthy is that you can note so for a small number of transistors, and that means that each of these little learning edges you can fit into a space of about 80 microns on the side. So building a learning edge, which is now actually getting close to the size of a neuron, which is pretty cool. And then you can stack them all together to design a chip, right? So this is the chip Sophia laid out. It's something like 100 edges, so 100 elements that can learn. It fits in a space just under a millimeter on the side. It's our first prototype chip. And we're really excited about this. So it's back now, right?
No.
So it's about to come back?
Yeah,
It should be like any week now.
Yeah.
So any week now, this will come back from our foundry. What we're really excited about is what we got out of simulation. So we characterized this a lot before we sent it out to be built. We estimated something like a picojoule per inference, which is a crazy tiny number. If you were to compare this to say like an industry chip, it's about the same. We should be nowhere in the ballpark, right? It's a $4 trillion company, graduate student and professor, and we really shouldn't even be close. And we're really excited to be able to test this. So with that, I'm on the dot. I think that's exactly the time you gave me, right? Yeah. Okay, and I'm happy to take questions. Thank you.